You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So Dan, you're a professional physicist, and so you probably get a ton of emails every single day, right?
Yeah, that's for sure.
But you were telling me that there's one kind of email that stands out.
Yeah, so I get like 10 of these emails a week, probably, or something like that on average. And these emails are always from someone who claims to have proven that some well-accepted facet of physics is just totally wrong. Maybe they think that Einstein's general theory of relativity is wrong, or quantum physics is wrong, or well, let me read one that I got here from somebody who's trying to argue that dark matter doesn't exist. So it says, "Dear astrophysicist, I've clearly demonstrated, based on the Kepler-Newton laws of gravitation, that dark matter does not exist. You may convince yourself of the latter if you take time to view the 45 slides included herein with a written presentation on PowerPoint.
Oh my God.
The first half, blah, 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 blah." Yeah, so, he took some textbook physics equations, applied it to a problem that like literally thousands of professional physicists have tried, and he gets a different answer than all the professionals and is pretty sure he's right and we're all wrong.
I like how he addressed you as astrophysicist. Like, he's not even customizing the emails enough to say your name.
Yeah, I assume a lot of my colleagues got this email.
Any chance that he's right?
I think it is exceedingly unlikely that the author of this particular email is correct. Do you want to hear another one?
Sure.
All right, here we go. This one doesn't even address anyone at the top. It just goes straight into the first paragraph. It says, "Okay, I've sent this to over 100 of the top minds in the world on this with no luck yet. No one will ever find dark matter on Earth's surface or deep underground. It won't exist there. Dark matter is a bubble of highly compressed space, highly energized with light." He goes on for a while, and then the closing is my favorite part. "Study my rationale and my equations. You will see that I'm correct, and then tell all Earth."
Sounds like an alien.
So I've got a third one here. This is one of my very favorites. I'm not even going to read the whole message, but the bottom line is at the end, they offer to tell me their theory of everything that they've deduced for the low, low price of $3.99. That's what cheap. It's a pretty good deal. But it doesn't make me any more confident that this guy's really got a workable theory of everything.
I'm confused. Is he trying to scam you with his physics theory or scam you out of $4?
I really don't know. Your guess is
That'd be a very elaborate scam for $4. Are a lot of the emails about similar topics, or are they all kind of random?
Well, I've noticed a pattern. Maybe, I don't know, something like half of all of the emails I get in this kind of vein are all about dark matter, specifically trying to argue that dark matter doesn't exist and that somehow we've just misunderstood the force of gravity instead.
Interesting. Are there any professional physicists who think that dark matter might not exist?
Well, there are a few, not very many. There's definitely what I would call a near consensus that dark matter exists. But there are a handful of people over the years who have thought long and hard about the possibility that gravity might not work the way we think it does. And because of that, we kind of get something like an illusion that dark matter exists. These ideas go under the umbrella term of MOND, or modified Newtonian dynamics.
So today we're going to dedicate our show to all of those email writers, and we're really going to dive into these theories of modified gravity. We'll talk about what they are, what their history is, and of course, why they are losing in popularity so strongly to the theory of dark matter. So hopefully by the end of this, you'll stop getting so many emails.
I think that's probably unlikely.
So let's start by talking about what MOND, or this theory of modified gravity, is.
So it goes back to about 1982, when the first version of MOND was proposed by this guy named Morihei Milgram. He took like one of the very first things you learn in your Physics 101 class And by which I mean the equation F equals ma, force equals mass times acceleration. Goes back to Isaac Newton, and he changed it. So basically, he changed it as follows. He says it works normally. The F equals ma holds under normal circumstances, but in circumstances where the acceleration is really, really small, it starts to go like F equals ma squared. So this happens when accelerations get smaller than about 10 to the minus 10 meters per second squared. So let me give you an impression of how small that is. So the Earth experienced acceleration from the sun's gravity, and that's at a level of about 6 times 10 to the minus 3. So we're talking about like, many millions of times more acceleration than where MOND really kicks in. And even if you go to the outskirts of the Milky Way, like to Pluto, the acceleration something like Pluto would experience is like 4 times 10 to the minus 6, still way bigger than the cutoff for MOND. But if you go to the whole Milky Way and ask how much acceleration is the sun experiencing as it orbits around the center of the Milky Way, then this is around the level where the effects of MOND start to kick in.
So Milgram suggested this modified gravity rule as a way to explain away some of the evidence for dark matter. And there's one particular piece of dark matter evidence that this theory of MOND is really good at explaining.
So this goes back to figures like Vera Rubin and others back in the 70s and in even early 80s, who were observing how stars and gas and things orbit around galaxies. And the more matter there is in those galaxies, the more mass in those galaxies, and the stronger the force of gravity is, the faster that you would expect those stars and gas to orbit around galaxies. In the same sense that if the sun were much, much heavier than it is, much more massive than it is, then the Earth could spin around it faster without flying off to infinity. So when Vera Rubin and others started to make these measurements, they found that these stars were zipping around galaxies, especially the stars in the outskirts of galaxies. They were moving really much too fast to explain it with the observed kinds of matter. In fact, it seemed pretty clear to them that most of the matter in these galaxies wasn't made of stars, gas, and dust and planets, but something else that they weren't seeing in their telescopes. We call that stuff dark matter.
So MOND was successful at explaining these galaxy rotations without the need for dark matter.
That was the first thing that MOND was designed to explain. And I would say it's fair to say that even to this day, that piece of the data, that piece of the evidence for dark matter could be explained by MOND. And they do one other thing that's pretty nice. There's this thing called the Tully-Fisher relationships that astronomers have known about for a long time. They just kind of noticed this. They didn't have an explanation for it. But they said that among spiral-shaped galaxies, the luminosities were proportional to their rotational velocity to the fourth power. And like that just kind of came out of nowhere. In MOND, it turns out that you can exactly predict that. That should be the right answer. So Milgram was, advocating MOND on the behalf of these two lines of evidence, the way that galaxies rotate and that they could explain this previously noticed Tully-Fisher relationship.
So MOND doesn't seem so bad so far. It has some good things to it.
Well, so far I've just talked about the good things. Maybe we should talk about some of the challenges. So I don't think anybody at that time thought that the kind of MOND that Milgram was talking about could be a complete theory. It has some pretty deep-seated problems. The theory doesn't obey certain principles that are pretty central to what we think about physics, like it doesn't conserve momentum or angular momentum. And it's really not compatible with general relativity, which by now has been, confirmed with very high levels of precision in any number of environments.
Let's break down those two problems a bit more. The first one, that MOND violates momentum conservation, ends up having some very troubling side effects.
Yeah, so it turns out that every conservation law in physics can be related to a symmetry of some kind. This goes back to Emmy Noether, an early 20th century mathematician who did really important work in this direction. We call it Noether's theorem. And in the case of momentum, the idea is that as long as there's no difference in my x, y, and z dimensions of space, as long as those are all treated on the same footing, then momentum has to be conserved. So the fact that Milgram's version of Mond doesn't respect that means there's something really weird going on with the nature of space that no one expected to be true.
And the second major problem is that this theory of Mond was incompatible with Einstein's theory of relativity.
Yeah, so as a starting point, he took F equals ma, which is not a relativistic equation. It's a equation of Newtonian physics. It's not true and not strictly true anyway in Einstein's theory. So he's starting from this kind of more primitive kind of physics and making changes to it. It wasn't obvious at all how you would do that in a way that was compatible with things we knew about general relativity. In the early 1980s, general relativity was a universally accepted theory. Like it wasn't contentious or controversial or speculative. I mean, everyone thinks of all physics theories as provisional. Someday they'll be replaced by something better. But this was about as solid of any physical theory that we had. So yes, it was a big deal that it didn't seem to be compatible with the general relativity and its principles.
But to be fair, even though this was a big problem for Mond, it wasn't necessarily the end of the world.
If we think back to the history of quantum mechanics, like we talked about in an earlier episode, the Schrodinger equation wasn't compatible with special relativity, and they overcame that by building things like the Dirac equation. So there was hope that something capturing the essence of Milgram's Mond theory could be built that was also compatible with relativity.
So physicists kept working on Mond to try to smooth out these problems and make a better theory.
It wasn't like a rush of many, many physicists trying to do it, but a few people tried to make progress in these directions. So in 1984, Milgram wrote a paper with Jacob Bekenstein where they introduced a different kind of Mond. They called it a quadratic Lagrangian theory. But basically, instead of starting with F equals ma, they start with this mathematical thing called a Lagrangian that if you take like, advanced undergrad mechanics, you will learn. And from that, they derived something kind of like Mond. This had some advantages. It conserves momentum and angular momentum and energy in a way that the original version of Mond didn't. It also respects something called the weak equivalence principle, which basically says the amount of gravitational mass something has is always going to be equal to the amount of inertial mass it has. So let me unpack that for a second. A gravitational mass is what makes something feel gravity or pull something toward it. And inertial mass is the kind of thing that takes a lot of force to accelerate or decelerate something. And as far as we know, everything's gravitational mass is always exactly equal to its inertial mass. That's kind of a foundational principle of general relativity. So it's a good thing that this new version of Mond respected that. And overall, this new theory made very similar predictions to the original version of Mond. It was within like 10% differences. And that was good enough to explain what we knew about galactic rotations at the time and things like this. So in a lot of respects, this was a big step forward, but it's also important to note that it still wasn't compatible with general relativity.
And this wasn't the only new theory of Mond.
So not long after that, Milgram and Bekenstein came up with yet another version of Mond. Now, instead of calling it a quadratic Lagrangian theory, they call it relativistic quadratic Lagrangian theory. So the name just keeps getting larger. And to kind of build this into a system that could potentially be compatible with general relativity, they had to do something pretty radical. They had to introduce two different things that we call metrics. So what a metric is like the rule that tells you how far apart in space or time 2 points in space-time are. So if I want to know how far it is from Chicago, where I am, to New York, where you are, Shalma, I need a metric to do that. I need some sort of rule to deduce distances.
So in two-dimensional flat space, the metric describing distances is just the familiar Pythagorean's theorem, the a squared plus b squared equals c squared. And that's because you can use it to say, for example, if I go 30 steps east and 20 steps north, how far away am I from my starting point? But in other more complicated geometries, like a curved space or a higher dimensional space, this metric will look a bit different. And in particular, in general relativity, you have a metric that describes distances not just in space, but in space-time. So this metric will tell you how far you've moved in both space and time.
And in all the physical theories that people usually study, there's just one metric. So if I give you 2 points in space or space and time, the distance, the interval between those points is the same no matter what kind of question you're asking about it. But in this weird version of MOND that was being proposed, they had 2 different metrics. One that told you things about the dynamics of matter and stuff moving through space, and another one that dictated effectively how far apart things were from each other from a gravitational perspective. So how much 2 things pulled on each other depended on a different distance than their motions did in a way. So we call this a bimetric theory because it has 2 metrics in play.
And this is problematic because if you have 2 metrics, it really messes up our notions of causality. It would be possible that one metric could say that 2 objects are close enough to be in causal contact, but another metric would say that they aren't. So it wouldn't be clear whether or not those 2 objects could actually causally affect each other.
Bimetric theories tend to be acausal. They tend to, lead to problems where you can kind of go backwards in time and screw up the past and lead to all sorts of logical paradoxes and all this stuff. And Milgram and Bekenstein knew this, and they tried to do some things with their theory to kind of protect it from these sort of acausal problems. But it turns out, we found out later, that the changes they made also screwed up things that tests we had done in the solar system, high precision tests of general relativity. So it seemed to break, successful predictions of general relativity when they tried to make the theory itself, logically self-consistent. Yet another problem faced by these kinds of MOND theories had to do with the phenomena we call gravitational lensing. So one way we, for example, measure the mass of things like galaxies and galaxies clusters is to look at how much light is deflected as it travels near these gravitational bodies. This is something that people have been trying to do for a long time, and lots of measurements have been made. But none of these theories predicted lensing in the way that was being observed. So, and also they didn't do a very good job at systems other than galaxies. It was designed to solve the dark matter problem on galaxy scales. But when you looked at galaxy clusters, they didn't look like what MOND predicted in other sorts of systems. So it was solving certain pieces of the problem, but leaving a lot of other issues very problematic. And that brings us to 2004, when Jacob Bekenstein presents a new version of MOND, a very exciting one at the time. I remember being very excited about this when it came out. It was kind of all the rage. But I was at Oxford at the time doing my first postdoc. So I was, fresh out of my PhD. I was studying dark matter. And then suddenly this theory came out. And I'd been taught long ago that MOND had all these problems and was almost certainly not true. And then this new version came out and it claimed to solve all these problems. And let's say those of us hunting dark matter got a little nervous for a little while. So this was a really complicated version of MOND. It's known as TeVeS, for tensor vector scalar gravity. It basically starts with GR, general relativity, and then it adds a bunch of stuff to it. It adds a couple of the extra things we call fields. It has a bunch of free parameters and even like a free function built into it. So it's super flexible. It can do a lot of different things depending on how you make these choices in the theory. Which is a good thing. It means you can, match to the data pretty well. But on the other hand, the downside is it doesn't have all that much predictive power. If you have a theory that can explain anything, then it also explains nothing.
So this new theory of MOND turned a lot of heads, but the excitement didn't last too long.
It was pretty quickly realized that galaxy clusters couldn't be explained by TeVeS, this TeVeS version of MOND. Early on, there were some papers showing that you could explain the patterns of light we saw in the cosmic microwave background with Tevis, but as those measurements got better, that stopped being the case. It just doesn't look the same. After all, dark matter formed the structures early in our universe's history. If you don't have dark matter, you just can't explain what we see in the cosmic microwave background, at least in the context of Tevis. And then there's one other thing called the matter power spectrum, which turns out to be really super powerful test of MOND. So this, I first appreciated this when my colleague at Fermilab, Scott Dodelson, back in 2011 wrote this paper, and he set me down and explained it. The paper is just simply called The Real Problem with MOND. So it comes down to this phenomenon known as baryon acoustic oscillations. Basically, the idea is that when the universe was young and hot and dense, there were sound waves propagating through the photons and protons and neutrons that made up this plasma throughout the entire universe. And these sound waves just rippled through it, and we can calculate what those should look like. And in a universe without dark matter, we should see those ripples in the large-scale structure of our universe today. And we do see them, but they're something like 30 times smaller than you would predict if there weren't dark matter. As it turns out, dark matter does the job of damping those sound waves, those ripples. It makes them smaller as time goes on, and it essentially erases this effect. Not entirely, but mostly. And the amount of these ripples that we see in our universe today, well, it matches the predictions of a universe with dark matter, but not one dictated by MOND, including Tevis.
So the evidence kept coming in and kept consistently supporting theories of dark matter over those of MOND. And one piece of new evidence was particularly impactful in moving support away from MOND into dark matter.
The thing that really convinced people to turn away from MOND was a system called the bullet cluster. So the bullet cluster is actually two clusters of galaxies. And they're gravitationally bound to each other. And something like 100 million years ago, they passed through each other. They kind of collided and went right straight through each other. And in 2006, some astronomers wrote this paper called A Direct Empirical Proof of the Existence of Dark Matter, where they compared where the gravity in those systems were, those clusters, to where the gas and other visible parts of the matter were. And importantly, they weren't in the same place. The gravity was in one place, namely the dark matter was in one place, where all the gas and other bulk of the visible matter was somewhere else. No MOND theory would predict that. MOND says that the gravity should be centered wherever the stuff is, and in a universe without dark matter, that's got to be where the gas and other visible stuff is. So I think it's clear, it was very clear immediately that the bullet cluster was going to be a big problem for MOND, and since then we've observed other systems like it. And I think that went a long way to, explaining the decline of MOND's popularity among scientists.
Yeah, that's some hard evidence to overcome. So do you think, given all that stuff, there are still any physicists who do seriously study MOND?
Oh, yeah. I mean, there aren't many of them. This is definitely a minority position. And there are a lot of very reasonable cosmologists and astronomers out there who are just trying to cover all the bases. They will acknowledge the arguments against MOND, and they acknowledge they're pretty compelling. But you never know. Some solution might come out that solves all these problems. So they just want to be complete. And if a small number of scientists are doing that, I think that's actually a pretty good strategy for the field to take. And then there are a small number of other people who seem to be true believers in MOND. I'm less likely to see eye to eye with them. I tend to think that their arguments aren't very compelling or interesting, but there aren't very many. There are just a handful of people like that.
Yeah, so I guess even though it's not popular, it's still worth studying in some capacity, just in case we miss something.
Yeah, I mean, you shouldn't give up on an idea just because some problem has emerged. You might find a solution to that problem one day, but at the same time, you don't want everybody working on something that's very unlikely to turn out to be true.
So at this point, Dan, how surprised would you be if it turns out that Mond really is the right answer and dark matter doesn't exist? You've spent a lot of time studying dark matter. How would you feel if dark matter didn't exist?
I mean, I would be shocked if I learned all of a sudden, if some paper came out tomorrow with a really convincing, compelling piece of evidence that dark matter doesn't exist and that Mond is right. And it comes from kind of two different lines of argument for me. One is that, like we've been saying, all the Mond theories that have been put forward so far have all these major problems. We have all these different lines of evidence in favor of dark matter in a variety of different ways. We see it in the way that galaxies rotate. We see it in clusters of galaxies. We see it in the structures of galaxies and clusters spread out the universe and how they formed and evolved. We see it in the cosmic microwave background. Everywhere we look, we see evidence of the same stuff in the same quantity with the same characteristics. Mond just can't do that. Let me use an analogy to kind of put it in context. Picture a detective who's trying to solve a murder case. The detective has a lot of solid evidence. They have a murder weapon with fingerprints on it, and the fingerprints point to somebody who has a really solid motive to have committed the murder. Everything about the data you have, the evidence you have, points towards one suspect. That's the dark matter interpretation of the data in my mind. But still, alternative explanations can't be strictly 100% ruled out. After all, maybe it's possible that the suspect you have has been framed in some sort of elaborate scheme to fabricate evidence that all points towards one direction when actually something else is true. Like Occam's razor definitely favors a simpler explanation over the more contrived one. And to me, dark matter is much simpler of an explanation than any version of Mond or that we've proposed or I think is likely to come out. But you can't say with certainty that one is the right answer, not until we directly detect the particles that make up dark matter. That's really the thing that will settle this debate for all time.
I just want to say that it's not because the physicists who are studying Mond or who came up with Mond are any less smart or less capable than the physicists who do dark matter, right? It's just evidence comes out over time and proves or disproves theories. And you can be a very smart physicist working on a theory that just happens to be disproven by the universe.
Well, absolutely. Jacob Bekenstein, who I've met, is by all accounts a brilliant man. He should have been very, very proud to have written down his Tevis theory and some of the other work he did. No doubt. I would be personally have been extremely proud to have written many of the papers that he's written over the course of his career.
Yeah, there's no shame in writing a theory that turns out to be wrong, I guess is what I'm saying.
The majority of my papers are wrong. It's not that they were wrong in light of what we knew at the time, but you write something down as a hypothesis, and that hypothesis is probably going to be falsified in the end. That's just how science works.
Yeah, it's a humbling process. And I think I understand to an extent how for some people it would maybe be easier to digest the idea that gravity, something that we know, gravity, is just different on different scales, than to assume that there is some kind of invisible matter that we've never seen called dark matter. Maybe I understand how that first one could be more intuitive to some people.
But as a particle physicist, I don't find it surprising at all that there would exist forms of matter that we can only detect through its gravity. After all, there are some kinds of particles like, electrons and quarks that we can detect through the electromagnetic force, and then others like neutrinos that we can't. And some other particles feel the strong or weak nuclear forces, and while others don't. The forces we know about don't affect all forms of matter. So from this point of view, it sounds incredibly plausible to me that there would be some particles out there, some forms of matter that don't experience any of the known forces other than gravity. And whatever that would be, we'd call that stuff dark matter. So it's from this point of view, I would even be a little surprised if something like dark matter didn't exist in our universe.
Yeah, I guess I never thought of it like that. I guess we're so used to, our human-centric brains observing the world, through light, that we forget that that's not the only way that you can see things and that things can interact. So hopefully all those email writers out there are satisfied with this episode. Hopefully we gave the pros and cons. I feel like we weren't totally negative towards Mond. I feel like we were fair.
Yeah, I think we're being fair. I'm not sure that will be the consensus view, but but we'll find out.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.